Today we will discuss bobbin building. So, to build a bobbin we have to wind the yarn. So, what is the winding principle? That is what we are going to discuss. As I said earlier that winding and twisting, these two operations are inseparable in ring spinning. Therefore, the elements which are used to twist the fibers, the same elements also helps in winding the yarn on the bobbin. So, what we are showing here in the diagram, that the ring is there, it is shown by this blue circle, and then the bobbin is also shown, which is little yellow in color, and the spindle exists at the center. The traveler is being shown, which is red in color in this particular diagram. So, the bobbin is turning in clockwise direction, and as a result of that the traveler is also turning in the clockwise directions. And why the traveler is turning? Because the traveler and the bobbin is connected by an element of yarn, and this element of yarn is being pulled, and the pulling force is helping to move the traveler on the ring. Now, both bobbin is rotating as well as traveler is rotating. So, therefore, the winding of yarn around the bobbin would need a relative motion between the bobbin and the winding element, in this case it is the traveler. Since both of them are rotating, if the both of them rotates at the same speed, then the relative speed will be 0, and in that case there is no chance of any winding. Winding theoretically is possible if they run against each other or they run in the same direction, but one must move faster than the other. Let the bobbin speed be n b and the traveler speed, let us say, is small n t. Then the relative speed between these two is either n b minus n t or n t minus n b, depending upon which one is running faster or which one is rotating faster. Either the bobbin or the winding element has to turn faster than the other, then only we will have relative speed and we will be able to wind the yarn. However, there are some more conditions to be met, and we will see that if we want to meet those conditions, then bobbin has to move faster than the traveler. The winding range has to be equal to the yarn delivery rate to avoid yarn breakage or slackness. Finally, the rate of winding, that is the length of yarn that we are going to wind on the bobbin, must be equal to the length of yarn being delivered by the front roller of the machine. That is yarn delivery rate, and if the bobbin diameter is dB, then V must be equal to n b minus n t into pi dB, assuming that the bobbin speed is more than the traveler speed. So, relative speed is n b minus n t, that multiplied by the circumference of the bobbin on which the yarn is going to wound, that will give me the rate of winding on the bobbin, and that must match the value V, that is the delivery rate. Now, the other condition is twist has to be kept constant, and if the twist, if you want to keep constant, the twisting element speed has to remain constant. From this argument we can say if the twisting element is traveler, then the traveler speed must be constant. but in this present case we will see that traveler speed is not constant, it really varies a bit, and not only that, the traveler speed is little less than the bobbin speed. We will see that gradually, actually we have already seen earlier that the speed difference that the traveler makes is actually so low with respect to the spindle or bobbin, that the twist that is inserted into the yarn hardly changes. That is, the variation that we would expect in twist because of traveler speed changing is so low that practically it can be ignored. We have shown it in the previous discussion that it was hardly close to 1%. So, for all practical purposes we can assume that traveler speed is constant, and hence the twisting rate is almost constant. As the yarn is laid onto the bobbin diameter that is dB will also grow, and hence the speed of one of the element must change, and in this case the speed of the traveler is made to change. The speed of the bobbin is maintained at a constant level. So, bobbin speed is constant and bobbin is fixed on the spindle, and therefore, the spindle speed is we keep constant, and we get the bobbin speed to remain also constant. The traveler speed actually keeps changing in order to wind the yarn that is being delivered from the front roller. This change in traveler speed get adjusted automatically. We do not need any control system as we had in the case of roving frame to reduce or to increase the speed of the bobbin there, in order to ensure that we are continuously winding the roving at a constant rate. Such kind of control on the speed of the traveler is not required. The traveler lags, and the lagging of the traveler gets automatically controlled by what? By the delivery of the yarn and because of the friction between ring and traveler. So, the traveler is lagging behind the bobbin because of two reasons. One is the friction, obviously friction must be there, and the second thing is continuous delivery of the yarn. The yarn element which is there between the from the front roller to the bobbin, this element of yarn is continuously being supplied, it is not held fixed, and because it is continuous delivery of the yarn, at the same time friction between ring and traveler will cause the traveler to lag behind the bobbin, and this lag gets automatically adjusted depending upon the diameter on which the yarn is being wound. So, the lag is basically the relative speed difference between bobbin and traveler causes the yarn to be wound on the bobbin. The lag is self adjusting in nature. This point is very, very important. It lags as much as is required to wind the yarn being delivered per unit time. So, when we need more lag, the speed of the traveler will be slowed down to that extent. When is less lag, speed of the traveler will be raised so that we get less lag. So, this is what is happening continuously. Changing of diameter will also change the tension at the point, that is the winding tension will also change, and hence the traveler speed will accordingly be adjusted. See, when we are going for lesser diameter, the tension, the winding tension as shown by this by F w will be more. When you are going for larger diameter, the tension will also be less. So, the value of F w is not constant and is also continuously changing depending upon what is the diameter of the bobbin on which the winding is going on. So, the lag is there and the lag gets automatically adjusted. The winding equation, if we try to write, then we can say that winding speed should be equal to spindle speed minus traveler speed, but winding rate is basically equal to yarn delivery rate, and we can write as we have written the equation earlier, V is Nb minus Nt into pi dB. At equilibrium, this equation will always hold good. And if I rewrite this equation, in order to find out what is my Nt speed of the traveler, we get Nt will be Nb minus V by pi dB. So, from equation 2, what we see that Nb is constant, bobbin speed is always constant. The delivery rate V is also constant, and therefore, pi is also constant. So, what keeps on changing is dB. dB will continually change as we grow from smaller diameter to larger diameter of the bobbin, and therefore, we can say from this equation that is dB is very high, then what was going to happen? V by pi dB is going to be low, and therefore, the difference between Nb and V by pi dB is going to be high. That is what the relationship is, and for different diameter of the bobbin, we can find out what is going to be the speed of the traveler. From there, we move on to geometry of the bobbin. I can show you a bobbin over here. I am showing this bobbin. This is a full bobbin, and here there is an empty bobbin. So, the empty bobbin is little tapered, which is quite visible from here. This is the bobbin which is hollow also, and it actually fits on the spindle. This is basically a press fit. You just press it, it will go down and it will be gripped by the spindle. And this is the full bobbin, where we see the yarn is there from bottom to the top, and this geometry we can say that roughly at the bottom it is little conical, top part also conical, and the central part from here to there is little cylindrical. So, the bottom part, the conicity of the top and bottom part little different. In some cases we will find generally the bottom part is little shorter, the tapered part of the bottom region is little shorter in comparison to the top region, and the bottom part in some bobbin building is going to be little curved in nature, which is not really visible here, but in some of the modern ring spinning machines you will find that the base part, the bottom part of the bobbin is not really so much of tapered, but little curved. This is the typical geometry of the bobbin. We will discuss why it is little curved also. So, this geometrical form of the bobbin is shown in this diagram, and what is there, that we have a conical part, we have a round base here, and we have a cylindrical part as shown in this diagram. The round base is 4 to 4.6 centimeter typically in length. The conical part is typically 5.5 to 6.2 centimeter in length. So, these are some typical values. So, K is going to be between 5.5 to 6.2 centimeter, and A is going to be 4.4 to 4.6 centimeter. Now, we are coming to the bobbin building, how the yarn is laid on the bobbin. First of all, what we see here is that the yarn is always deposited in the form of layers on a conical surface. So, first we try to quickly develop a conical surface on the bobbin. The bobbin is, as it has been shown, that it is though little tapered, but we want to generate layers in the form of cones. Why do you do it? It facilitates high speed unwinding. We want to create such a conical surface because this helps us for high speed unwinding of the yarn in the subsequent process. That is why the conical nature of the surface, like you see from here, this is the conical. So, initially we quickly try to build a conical face on which, or a conical surface on which rest of the layers will be laid, starting from bottom of the bobbin to the top part of the bobbin. The reason is high speed unwinding. Bobbin building therefore has two phases. First phase is called base building, that is, we are trying to going to create the base. That base building is from almost from here to there. This part is the base building part. From here to there, we basically trying to base the build. You see the way the layers are being formed. The diagram clearly shows that how the successive layers, this is the first layer, then this is the second layer, this is the third layer, this is the fourth layer, then the fifth layer, and the sixth layer onwards, a conical surface has been built, as it is shown in this diagram. Second phase is continuous deposition of yarn on the conical surface. So, base building basically means creation of a conical surface, and then once it is done, now onwards the yarn will be always laid on a conical surface and will keep generating layers after layer till we reach to the top part of the bobbin. For filling the entire bobbin surface with yarn, the ring rail acts as a guide. And if I want to lay the yarn on the bobbin surface, the yarn has to be guided. So, there is a guide, and in this case the ring rail acts as a guide. The ring rail and the traveller together acting as a guide. So, ring rail therefore is not held stationary, it keeps on moving along the length of the yarn. It moves up and down continuously. Bobbin or the corp is built bottom to top by superimposing many conical layers. The conicity of the conical layer changes gradually initially and becomes constant thereafter. As we have seen in the previous diagram, that if we look back, that this conicity, the very first layer, second layer, third layer, fourth layer, if we observe, then we will see that the angle is gradually changing of these layers, and by the time we reach the sixth layer, then onwards the conicity is constant. Now, classification of layers. There are two types of layer that we form. One is known binding layer and the other one is known as main layer. Main layer is formed during slow raising of the ring rail. See, the yarn is continuously being delivered. The ring rail is acting as a guide and the ring rail is going up and then coming down, going up and coming down. But it is not going from base to the top of the bobbin as we do it in the case of building roving bobbin. There the entire bobbin rail moves up and down and the roving is laid from bottom to top, but in this case this is not what is not done. We do not lay the yarn in the form of roving wheel. We are laying the yarn in short strokes over a shorter length, and when that length gets filled up, we go to the next position. So, in short strokes we keep on laying the yarn. This is we do it because we need to create or have less tension variation when we are actually unwinding the yarn at high speed. Therefore, what we have, two types of layers are formed. One is called main layer, which is done for slow raising of the ring rail. That basically means the ring rail is not moving at a constant speed or constant velocity. So, if the ring rail moves slowly, the windings are close to each other as shown in this diagram. You look at this diagram where this lines shows that the coils are basically very close to each other, the yarns are very close to each other because ring rail is moving slowly. But then when the ring rail is moving down, then it moves down fast, and when it moves down fast, the angles that these yarns are making with respect to the axis of the bobbin, they are different. So, they are called cross layers or binding layers. They are more inclined and they form because of rapidly lowering the ring rail. So, we need to have these two types of layer. We will discuss why we need these two types of layer. The binding layer separates successive main layers and thus prevent several main layers being pulled out simultaneously at high speed withdrawal of yarn during winding on cone or cheese. So, this is more to facilitate the winding process subsequently. To avoid the sloughing off of the coils from the bobbin, we need to have winding layer and binding layer, winding layer and binding layer continuously, so that the layers remain separated from each other. And how we make them keep them separated? By having the wrap angles different from each other, and this is achieved by adjusting the speed of the ring rail. So, ring rail moves up slowly, but comes down fast. Now, nature of ring rail movement. The diagram on the right hand side is showing how the ring rail is moving. As I already discussed, that it moves in short strokes. It is not that you are going from bottom to the top and then coming down again going to the top. That is the kind of movement we do it in the case of roving building, but in the case of ring rail movement or making the bobbin or for ring spinning, the movement is shown in this diagram. These are in short strokes as shown here. The stroke length is known as chase length. So, you see here the blue line shows it is going up and the orange line shows it is coming down, again it is going up, coming down. This manner it moves up like this till it reaches to the its final destination. So, chase length is shown here, the distance over which the ring rail is moving, that is called the chase length, is roughly equal to the ring diameter. After each layer formation, winding and binding layer, the starting point is shifted by a small amount h. You see here, starting point here is this, then it becomes here, then it goes there, then it goes like that. So, this starting point after each cycle of movement of the ring rail is shifted upwards, and this amount of shift in this case is h. It causes both top and bottom chases, that is the conical part, to be formed. That is why gradually we shift it, and also we know that unless we shift it, we will not be able to cover the entire surface of the bobbin, because gradually we have to cover the entire surface of the bobbin with yarn. Now, we will discuss base building part of the yarn of the bobbin. See, diagram is shown here how the base gets formed. As we have shown that the base is little curved in nature. How we are forming the base? The length of yarn wound per layer is always constant. See, for every cycle of movement, the rail takes same time always, and therefore, during that time, that upward stroke and downward stroke, in this time, whatever length is being delivered by the machine, that is the drafting system, remains constant, that does not change. If the length remains same, the volume of the yarn also will remain same. Now, deposition of the double layer, that is winding and binding layer, begins on a tube of small diameter D1. First, we start on a tube of small diameter D1. Now, the average diameter increases with each new layer deposition. So, let us say the diameter of the tube is, let us say, is D0, this is the diameter, the bare tube, just D0, and then as you lay the first layer, the average diameter is D1, and you see the layer thickness, this is the layer thickness now, which is quite thick. So, if we know the volume of the yarn that we have to accommodate on the bobbin, and if we know the stroke length, we will be able to find out this yarn is being wound on a bare tube of diameter D0, and therefore, how much is going to be the thickness of this layer, that also can be easily worked out. Let us say as a result the thickness change is, let us say this is the 0 to B1, that is the increase in thickness due to formation of the very fast layer. Now, when I am depositing the next layer on the top of the very first layer, the second layer is actually being deposited on an average diameter of basically D2 now. Now, because now the volume of the yarn is same, but the diameter is increased, therefore, thickness of this layer is going to be less than the previous one, and the thickness, therefore, this thickness, if you look at it, it changes. Earlier it was from 0 to B1, now it becomes B1 to B2, and B1 to B2 thickness is less than 0 to B1. And then when you go for the third layer formation on the top of the previous two layers, the increase in thickness becomes B2 to B3, and when you go to the fourth layer, then it becomes from B3 to B4. So, if you look at the layer thickness one after the other, the thickness keeps on reducing. And what is happening as a result of that? If I join these by a line as shown here, the outline looks like a curved line, and hence we get a base which is curved in nature. Reason that successive layers are being laid on a larger diameter, and hence thickness is continuously reducing, and therefore, when the outline that gets formed looks like a curved line. This is the reason a curved profile will generally gets built up. Which stroke to be used for winding and binding layer formation? Which stroke to be used? See, this question also comes that while the ring rail is moving up slowly, we are forming the main layer or winding layers. When it is coming down first, we are forming the binding layers. If we reverse this, what is going to happen? That instead of going up slowly, I going up fast. The ring rail moves up fast, but comes down slowly. In that case also, we will be able to form the layers. As far as the bobbin building is concerned, there will not be any problem. But where the problem could be, let us try to examine it now. So, strokes in this case mean upward stroke and downward stroke. So, should we build the winding layer during upward stroke, or should we build them in the downward stroke? Now, in this diagram, what is being shown is the part of the bobbin, and coil is being shown. The tapered part, the coils are shown by the blue lines. So, this side is the nose part, and this side we call it the shoulder part of a chase. At any point of time, if we look at the bobbin, suppose this is the bobbin, you will always find that from here to there, this part we call it shoulder and this part we call it nose. If I remove the yarn, let us say from here to there, we will still find a conical part always, because we have generated the conical part right at the time of base building, then onwards always we had the conical parts. So, whether it is here or there, the conical part will be always there. Now, so shoulder is this part for the diameter is more, and nose is the part for the diameter is less. So, after formation of the bobbin, it goes for unwinding, because we have to make large cheese or cone on the winding machine. So, in the winding machine, these cops are put and the yarn is withdrawn at high speed. So, when the yarn is withdrawn at high speed, as it is shown here, if this is the direction of withdrawn, during unwinding at high speed, the coils being unwound may pull the coils ahead of it and lead to sloughing off of the coils. So, if we generate the coils in this direction as shown, slow downward traverse, if we do it, then while unwinding, I will unwind this coil first and then succeeding coils will be unwound. When this is being removed at a very high speed, this coil will basically slip and will come into contact with this coil and this coil and these coils, and as a result a bunch of coils will be removed, and from the surface, from the conical surface, and this bunch of coil when it gets removed, we call it sloughing off, they get entangled and the yarn is going to break. That is the problem that we are facing. If we create these winding layers while the ring rail is going down, that is in the downward stroke. Now, if we change it, the next diagram shows it, that is we first form the shoulder and go this way, slow upward traverse if we do, then while unwinding, this is the coil which is going to be removed first, but since the next coil is behind it, this coil is not going to interfere with the coil which is behind it. Similarly, this coil is not going to interfere with the coil is behind it. Therefore, the possibilities of slopping off will be very less or almost maybe absent. So, during unwinding at high speed, the coils being unwound will not pull the coil behind it, and hence will not lead to slopping off of coils. So, we will be able to avoid the slopping off phenomena which sometimes we face at high speed unwinding of the cup during the winding process while we are making cones or cheeses. To avoid this, this is what should be preferred. Now comes, we will further discuss the formation of the conical layers. What happens? As we have discussed, the ring rail does not move at a constant velocity, it does not move with uniform velocity while it is going up also. While it is coming down, it is also not moving at constant velocity. Ring rail does not move with uniform velocity, it moves slowly with increasing speed during upward movement and quickly with decreasing speed during downward movement. So, that means there is an acceleration basically, that while it is moving up, it is accelerating, while it is moving down, it is also accelerating, speed is going down faster, it is decelerating. So, upward movement speed is near the tip is higher than at the base. Therefore, if I move, suppose if we move the ring rail faster as it is going from bottom to top part of a chase, what will happen as a result of this? Ring rail will spend less time near the tip of its journey than near the base. So, if speed spend less time, less material will be deposited near the tip and the layer will be thinner at the tip. That is what is shown in this diagram here. See the layer, the first layer, if this is the first layer being built, first layer, the ring rail is moving faster, gradually is going from base to, as it is going up, speed is increasing. So, spending less time near the top of its journey and more time at the base, and hence here it gets more yarn to be laid. So, the layer thickness is more at the base and less at the top, and hence this increase in layer thickness is not going to be uniform also from, we can say, shoulder to nose, in this case that is from bottom to top part of its run. And this is going to happen. So, the next layer, when you build first layer, second layer is built over here, part of it is on the first layer. So, it, and we shift the initial starting point. So, we have shifted. So, the first layer is here, the second layer starts from, not from in this page, second layer starts from here. So, this is the amount of shift which is h, as it was shown earlier, start from here, but this part is being built on the top of the previous layer, but it goes little up here. What will happen? Layer 2 will be little thinner than layer 1. So, layer 3 will be also little thinner than layer 2. So, this way gradually the layer thickness will change as we go from bottom to top. now let us say the speed at the top be 3 times slower than at the bottom. Is not slower, it should be faster. Speed at the top be 3 times faster than at the bottom. So, first layer would correspond a trapezium as shown here. So, the layer thickness, if it is B1 at the bottom, it is going to be B1 by 3 at the top. So, this is the very first layer, and let us say the speed changes by 3 times. So, speed becomes faster by 3 times, and therefore, we actually lay less yarn here. Here it is moving slowly, so we put more yarn over here. So, if we compare B1, whatever is the B1 here, at the top is going to be B1 by 3. Second layer will form on the top of the first layer, owing to shift of the starting point, the upper portion of the new layer will form on bare bobbin. See, this part of the second layer, this is layer 2, this part is going to, only this part is going to be formed on the bare bobbin, the rest of the part of the second layer is forming on the previous layer. Therefore, for the second layer, if the thickness at the bottom is B2, B2 will be less than B1, but at the top it is going to be of same thickness B1 by 3, because the top part of the layer 2 has been laid on bare bobbin. So, the top part of layer 2 is also going to be exactly equal to B1 by 3. Bottom part will be little thinner comparison to B1, and gradually it is tapering, and as it going to the top thickness is gradually changing, and it is almost taking the this kind of shape. So, this way layer after layer will be formed, and we see that it will be like this. B4 is less than B3, which is less than B2, which is less than B1, that is the bottom part, but the top part is also always going to be B1 by 3, because it is going to be laid on the bare bobbin for all these layers. And what we see, look at the way the layer geometry is changing, geometrical shape of the layer is changing. The trapezia will continuously narrow down. This is a trapezia, first, second, each layer is basically a trapezium, and as we progress, keep on building the base, keep on laying the yarn one on the top of the other, the trapezia will continuously narrow down. So, it is becoming thinner and thinner, and at some stage the trapezia will going to be a parallelogram, as it is shown here, that by the time we reach to this point, let us say this layer and this layer, it looks like a parallelogram now, because this layer is actually being laid on a diameter which is this much thick. So, it will be very, very thin there. So, trapezia will be look like a parallelogram, and thickness at the lower part and top part will be exactly same. And now onwards, no change will take place, conical layers will be laid one after the other, because by that time we have formed the conical layer, the conical surface. So, and the base will look like, if I join them by a line, the profile will look perfectly round, and we have built a surface now which is here, which will look like, this surface is going to look like a conical surface. So, now onwards we are continuously laying yarn on a conical surface. So, this is called the base building part, and rest of the part we are always laying yarn on a conical surface. Now, so for laying the yarn, what we need? We have to move the ring rail and traveler combination acting as a guide for laying the yarn on the bobbin. So, ring rail has to move up and down. So, we have seen the way ring rail should move as it is depicted in this diagram also, the ring rail movement. But along with the rail limb, the ring rail performs two motions. Therefore, a continuous up and down movement for winding and binding coil formation that we have observed, because we need two types of coils, so that the coils remain separated from each other, and it helps us in high speed unwinding. And for that we need continuous up and down movement of the ring rail to make winding and binding layers. And the other thing is gradual raising of the ring rail in small steps after each layer formation to cover the entire bobbin surface, and that is why these are the steps. So, first layer starts from here, second layer starts from there, then this layer, then this layer. So, the starting point is moving up and up. This is what is, these two type of movement is required, and we have a mechanism by which this movement is generated by cam and by lever. We will see that also. The consequence of this is this kind of movement, the consequence is the yarn tension variation due to change in balloon size is going to be very high. Yarn tension will vary, because when I am winding here, I have a very big balloon. The yarn element is from here to there where we have the lappet guide. So, the balloon is very large when I am winding near the bottom part of the bobbin. Besides, the tension varies because of winding on diameter keeps on changing, because for each layer formation I am winding on a very large diameter, which we call the shoulder part of the bobbin, and we are also winding on the bare bobbin surface, which we call nose part of the chase. So, there is a continuous change in the winding on diameter. Because of that also tension will change. We will discuss how tension is affected by the change of winding on diameter. The balloon size also, because ultimately we have to rotate the loop of yarn against air, and therefore, we need some extra energy, and we need to develop some tension. The yarn has to carry the weight of the traveler also. The traveler is also facing resistance, friction resistance from the ring, but all of these forces are acting finally on the yarn, and therefore, the yarn loop which is rotating is always under tension. So, in a given time, this tension mainly depends upon the length of the balloon, the weight of the traveler, and the speed. So, length of the balloon is continually changing because the ring rail is going up and down, and as finally we are reaching to the top of the bobbin, at some point of time the balloon diameter will be very small, and therefore, tension we can say is maximum when you are winding near the bottom part of the bobbin, but while I am winding on the top part of the bobbin, the tension must have reduced quite a lot, because by that time the balloon size has gone down in terms of its length. So, this makes a lot of tension variation. This is what we need to also control. So, balloon control ring and lappet guide perform exactly similar motion as that of the ring rail. What we have here is a balloon control ring which is here, and there is a lappet guide we have seen that as the yarn leaves the front roller nib, it passes through a lappet guide which is positioned exactly on the top of the spindle, and then there is a balloon control ring which controls the size of the balloon. It actually makes a big balloon into two parts, there is two sub balloons gets formed. So, what we do that we also keep moving the balloon control ring, it has gone from here to there, this movement we allow. Similarly, the lappet guide also moves like this. So, ring rail moves slowly with increasing speed during upward movement and quickly with decreasing speed during downward movement. The ratio of length of yarn in winding and binding coils or binding layer is 2:1. Total length of yarn in winding and binding layer is varies between 4 to 5 meter approximately. So, in one cycle of the movement of the ring rail, we are winding 4 to 5 meter of yarn. The traverse stroke, the stroke length, we call it chase length, is 15 to 18% more than the ring diameter in ideal cases. So, L you can say chase length is 1.15 into dr, where dr is the diameter of the ring. This is ideal, sometimes we keep it close to this also. So, it is 1.15 or 1. Maximum 1.18 we can go. So, what we do that we keep the balloon control ring and lappet guide both are given motion which is in sympathy to the motion of the ring. So, as the ring rail is moving up and up, the balloon control ring also move up and up, the lappet guide will also move up and up. But obviously, there is a limit how far it can be move up, and hence the total movement of the ring rail is much more in comparison to total movement of the balloon control ring. See, ring rail is moving how far? From here, from this position it goes up to this position. So, this is the total upward movement of the ring rail from starting of building to the end. Balloon control ring starts some from here and it goes let us there. So, this movement is from here to there, this much is its movement. Lappet movement it starts from here and it goes up to there. So, this is the movement of the lappet for the entire bobbin building period. So, they are all moved up as the ring rail is moving up also, and this is all to take care of the balloon size variation. We want to minimize the variation of the size. Obviously, we just can't eliminate totally the variation, but we want to minimize the variation. Now, we go to the building motion. That is, we have till now we have discussed what we need to do in order to form a cup. Now, comes how it is done, how it is achieved, that is the mechanism part now we are going to discuss. So, the mechanism part is called building motion. A sketch is given on the left hand side showing the way the mechanism is going to work. What we see here is that there is a lever rail which is fulcrumed over here, and on the lever there is a small, there is a cam over here and there is a cam follower also, and the other end of the lever there is a drum, we call it chain drum. On the end of the chain drum there is a ratchet wheel. The chain drum is connected to another, we can say a drum which is D1 mounted on the shaft S. Okay. The other end of the shaft, you see there are two pulleys or two drum, we can say D2 and D3. D2 is connected to the ring rail by a chain. This is the chain. So, the D3 is connected to the lappet and balloon control ring together. This is the simple the sketch which is describing the way the motion of the cam is transmitted to the ring rail, to the balloon control ring and to the lappet. Now, the cam is giving rotation from, so the cam gets its drive from motor through a chain of gears and it rotates at a constant speed. Now, if the cam rotates, what is going to happen? The cam is going to press the cam forward. This is the cam forward. So, cam forward will be pressed. As it is pressed, because it is always in contact with the cam, the forward is always in contact with the cam. So, as cam rotates, the forward will be pressed, and so cam, if you see from here to there, if we will go, the diameter is very large, from here to there diameter is less. So, depending upon which part of the cam is in contact with the cam forward, the lever will be depressed. As the lever is depressed, the chain drum will also be depressed. It will go down or it will move up depending upon where the contact is established between the cam and the cam forward. So, as the cam rotates, the lever we can imagine is moving up and down as shown by this double sided arrow, and chain drum will as a result move up and down, and hence this chain K which is shown, it will be pulled sometimes and pushed sometimes. The chain is connected or it is wrapped over a drum which is D1. So, as a result of this, what is going to happen is this, that the drum D1 is going to rotate in clockwise direction and in anti-clockwise directions, because the chain drum is going down sometimes, is moving up sometimes. So, with the cam rotation is transmitted through lever and chain K to the drum D1, and the drum D1 responds in terms of rotating clockwise and anti-clockwise directions. This is transmitted through the shaft S to two different drums or pulleys called D2 and D3. D2 as in turn connected to ring rail. Therefore, what happens that as it rotates, this chain will cause the ring rail to move up and down in sympathy. The other one, the chain connecting D3 and the lappet and the BCR, both of them will also move up and down in sympathy depending upon direction in which the shaft S is turning. So, the cam rotation of the cam is finally transmitted to the ring rail and the BCR, that is balloon control ring, and the lappet guide in terms of traverse movement up and down. That is what is done by this. At the same time, we have to see the role of the ratchet wheel and the catch. what it does? Each time the lever moves up and down, it presses a catch C. This catch C is pressed and rotate the ratchet wheel connected to the drum chain. As a result, what happens that this catch will engage the ratchet wheel and it will cause the ratchet wheel to turn by 1/10, and as it turns, the chain drum will also rotate by a similar amount. The drum will rotate a bit and it will, what is the result? The chain will be wound on the drum by a very small amount. So, depending upon whether it catch is moving the ratchet wheel by 1 tooth or 2 tooth, which can be adjusted, the rotation of this chain drum will vary. But for each time the lever comes down and moves up, ratchet wheel will turn by 1/10 or 2/10 depending upon the setting, and hence this chain K is going to be wound, and if the chain K is wound on this chain drum, what is the result of this? Shortening of the chain rotates the disc D1 shaft S, and therefore, discs D2 and D3. As a result, the position of the ring rail is raised a bit. Every time the chain is shortened by few millimeter, the ring rail will permanently move up also by some millimeters. So, as we have discussed earlier that the starting point of the winding layer formation keeps changing with time. This is how it is achieved, by shortening the chain by a small amount, and we are achieving it with the help of the ratchet wheel and the catch. So, this is what the mechanism is. The other thing is, we will discuss a bit about the base building, which is also special, because if we go to any ring spinning machine and observe the building mechanism part, then you will see that there is some additional feature in the building motion which is there to help building the base part faster, and that is why we see, we have written it here. What we see here in this diagram is focus on this N, is a small cam which is mounted on the drum D1. The purpose of this is to help in building the base faster, or we want to make the base more round. If the base is conical, it basically means our package content is going to be less. If the base is rounded, it basically means I will be able to accommodate more yarn there, therefore, package content can be improved, and hence the base building is there. Ring rail movement is accomplished due to rotation of the builder cam, as we have discussed it earlier. So, this is the builder cam here, this is the lever. So, we have already discussed which presses the lever, and thus disc D1 is continually turned clockwise and anti-clockwise. So, as this cam is pressing this lever and then from this lever it goes there, what happens that this chain is pulled, and as a result this is transmitted to the ring rail. This entire chain movement is getting transmitted, as we have discussed earlier. The one thing that we see it here, that on disc D1 there exists a small cam N. This is the cam which projects out of the periphery of the disc. This cam is projecting out a bit from the periphery of the disc. At the start of winding, the disc D1 deflects the chain, and as a result the chain movement upon raising the lever rail is not fully transferred to the ring rail. Part of it is lost as deflection at N. So, what happens when we start the winding process? At that time the way this cam is set, that it will deflect this chain. This is the chain K shown here, deflection is maximum there at the beginning of the winding process. So, as a result what happens when the chain is moving up, because the lever is moving up, the entire chain movement is not transmitted to the ring rail, it is going to be taken up by the cam N, because the cam is deflected and therefore, part of this is getting lost. Entire upward movement of the chain is not getting transmitted to the ring rail. That means, the ring rail stroke length is going to be less by having this. Traverse stroke is therefore going to be shorter initially. So, what happens gradually? As the yarn delivered per stroke remains same, but stroke length we have reduced initially, the volume per layer is going to increase, generating a curvature. Volume per layer, or you can say layer thickness is going to increase, because length of yarn is same. I am trying to accommodate the same length on a shorter part of the bobbin. Basically, that is what we are trying to do. Length is suppose 5 meter, we want to wind in one full stroke, but 5 meter is wound on a lesser area of the bobbin, the ring rail is not moving to this fullest amount, the fullest stroke length, and therefore, if I want to wind the same yarn on a smaller surface, the thickness is going to increase. Therefore, volume per layer you say is going to increase. As spinning will progress, that is the bobbin building is going on, the chain take up disc T steadily turn to the left in small steps. This disc here is going to wind this chain is going like this, you see the path as it was shown here with this help of a ratchet and a pawl or a catch kind of mechanism. This chain is continuously wound around this by small amount. Every time the builder cam is pressing it, little bit amount is always wound. Therefore, it shortening the chain length K results the disc D1 to turn in small steps. When I do this, the disc D1 will turn in small steps to the right. So, disc D1 will move in the right direction, because the chain is pulled, because it is getting wound on T, the disc T in this case. So, as the disc D1 keeps turning in the clockwise direction, what will happen? A time will come when this projecting part, that is cam, will be out of line from this, from the line of action of the chain. That means, this will come somewhere here. Let us say this will move somewhere here after some time. When it moves somewhere here, the chain is no more deflected by this projecting out part, which is a small cam, and it is no more effective. The purpose of the small cam is lost by that time, because we do not need now to use it. So, initial part we want to use it, we place it in such a way that chain is deflected as shown over here, but as we build few layers, maybe 10 layers, maybe 15 layers, this part will move somewhere here from, and then it is no more deflecting the chain. So, the entire chain movement will be transmitted to the ring rail. So, normal movement of the ring rail will start and it will continue. That is how it is done. Can I calculate the length of chase if I know these, if we have this diagram with us and if we measure these various dimensions that is required, then we can find out what is going to be the chase length. Length of chase small l is going to be basically lift of the chain on drum D2. Whatever is the lift of the chain on drum D2, that is this, that is connected to the ring rail. Ring rail will also move the same amount. So, basically I need to know what is the lift of the chain on drum D2 because of the rotation of the cam. So, cam, let us say, depresses the cam ball on the lever L by a small amount d. As cam depresses the cam ball on the lever L, the chain drum moves down, this drum will move down. So, it will be like this. So, this is the fulcrum position. From here to there, this is x, from here to there, let us say this is y, and this is the chain drum moves up and down by this much amount, and this is the amount by which this is the location of the ball. So, the ball is movement by this. So, this is basically your d, let us say this depression by the of the cam ball, let us say that is d, and this is over here, and we want to know what is this z. So, from similar angle we can easily find out how much z will be. It is going to be d into x plus y by x. As chain drum is pulled down, shaft s will rotate. If it is pulled down by z, we have to find out what is the rotation of the shaft s. The chain is moving or is wrapped over a pulley or a drum or disc, whatever we say, which is d1. So, the rotation of the shaft is going to be z into d1 by 2. A small d1 is basically representing the diameter of the disc d1. Is going to be 2z by d1. From there, we can find out, if you look at this. So, lift of chain L is going to be now theta into d2 by 2. If I know theta multiplied by d2 by 2, which is r, is going to be the lift over here of this chain, which is equal to the chase length. So, that if we put the value of, replace theta by how much, 2z by d1, and then d2 by 2 we multiply, we get this relationship. So, if we know all these values, we can find out how much is going to be the chase length L, and if we want to adjust this chase length, we know which parameters are basically important. Sometimes we may need to adjust chase length by suppose few millimeter, 5 millimeters more or 5 millimeter less. The question that comes to the mind is which parameter of this mechanism are going to change. So, we know what parameters are going to affect it, and all those parameters are in a way responsible in deciding the length of chase, and whichever parameter is easy to change or most convenient to change, we can change it in order to adjust the length of chase. Similarly, length of yarn wound in winding and binding layer, we can also find out easily. Each cycle of movement corresponds to one revolution of the builder cam. Let us say 2/3 rotation of the cam be used for winding and 1/3 for binding layer formation. If the speed of the cam is n, yarn delivery rate is v, the length of yarn delivered per cam rotation is going to be v by n. So, length in winding layer is going to be how much, 2/3 into v by n, because in one revolution of the cam this much is wound. Out of that 2/3 is used for winding layer formation. So, 2/3 of V by N will be length of winding layer, and length of binding layer is going to be therefore 1/3 of V by N. This is how we can easily calculate, provided we know the speed of the cam, that we need to find out. If we have the gearing diagram, we can find it out, and also we can find out from the gearing diagram what is the delivery rate of the yarn. If these two things are known to us, we can easily calculate theoretically how much yarn length is going for winding layer formation and how much is going for binding layer formations. This all depends upon the way the cam has been designed. It all depends upon the way the cam profile. With this, we close this session. Thank you.